When I was little, I loved origami. I used to fold a paper in half over and over and over again, till I couldn't fold it anymore. But once A4 size piece of paper became as small as my fingertip. Now imagine, if we took a piece of paper that is bigger than our sun, and we fold it in half over and over and over again, until it's as small as a grain of sand. The paper's mass hasn't changed, but its density is now so extreme that the resulting gravitational pull is unstoppable, creating a black hole. Today, I want to dive into one of the biggest questions it creates, the information paradox, starting with some background information on the black hole. Then we will talk about the paradox itself. Then we will talk about some resolutions, along with the most agreed one right now. Black hole. To picture how it works, imagine a space as a giant stretchy mattress. When you place a heavy ball on it, like a star, the mattress bends inward. The bending is gravity. But if you place something unbelievably heavy, the mattress stretched out into the bottomless funnel. And that's a black hole, a region where gravity curves space so deeply that anything nearby falls in and can't come back out. But here's where things get strange. In 1976, physicist Stephen Hawking published a paper in Physical Review D through the American Physical Society, raising what's now called the black hole information paradox. He asked the questions: what happened to the information about matter that falls into the black hole when the black hole eventually evaporates? But why is this question so crucial? Well, in quantum mechanics, there is an absolute rule. Information about a system, its quantum blueprints, can never be truly destroyed. For instance, if I burn a book, the page turns into smoke and ash. I can't read the story anymore, but all the tiny detail about the ink and the paper, every atom and molecules are still somewhere in the smoke, ashes, and heat. So technically, nothing is truly lost. It's just scrambled beyond recognition. Now here's the twist. In 1974, Stephen Hawking discovered that black hole actually isn't perfectly black. They slowly emit tiny amounts of radiation, also known as Hawking radiation, over a very long time. That makes the black hole shrink and eventually, well, disappear. The radiation, however, looks completely random, meaning it doesn't seem to carry any trace of what fills into the black hole. So when a black hole finally evaporates, it seems as if all the information about everything that fell in, the stars, planets, and even light, is just gone forever. That's a huge problem because it breaks the most important rule that I just mentioned: information is never destroyed. For decades, scientists searched for an answer. Some thought the black hole might leave behind a tiny leftover bits that stores the data. Others suggest that the information is somehow imprinted on the surface of the black hole. But today, the leading idea is that the information slowly leaks out through the Hawking radiation itself. You might ask, but how? We just said that the information looks completely random. Well, at first glance, it is random. But in reality, the information is hidden in tiny patterns within the radiation. A way scientists understand this is through something called a replica wormhole method. Think of it as making many copies of the same puzzle and realizing that tiny matching pieces reveal hidden patterns. The results of their calculations show strong evidence that information does, in fact, escape over time. In the end, black holes might not destroy information as Hawking once believed. Instead, they act more like shredders. They mix up information beyond recognitions, but never truly destroy it. And with that, the fundamental rule of our science still stand tall, and the past 100 years of physics haven't gone to waste. Thank you, everyone.